Welcome to Chapter 8. I'd like to go through a handful of worked examples with you. Just follow along with me. This is our first example. It reads, write and balance the chemical equation for the aqueous reaction of barium hydroxide and perchloric acid to produce aqueous barium perchlorate and water. Strategy here is to set it up with the reactants and the product side. Make sure that you're writing the correct chemical formula given the name. So we have barium hydroxide, which is BaOH in parentheses 2. Perchloric acid is HClO4. The products, barium perchlorate is BaClO4 in parentheses here 2. And water, H2O. All of these will be aqueous, except water is going to be labeled as with an L because it's a pure liquid. When water is in liquid state, it'll always have the L. Most salts and acids will be AQ if they are in solution. So then you can generate this formula with BaOH2, AQ represents aqueous. The most common solvent is water, so these will be dissolved in water. Here's perchloric acid. Forward reaction arrow are barium perchlorate with the aqueous label and water. Make a table and keep track of how many elements you have on each side. One thing I recommend doing is if you have a polyatomic ion, like the perchlorate, and it's on both sides, actually count that as an individual rather than separating it out. And it even mentions this. Perchlorate ions appear on both sides of the equation, so count them as units rather than count the individual atoms they contain. So following this step by step, here's our tally. We have barium. There's 1 on each side. The oxygens, leaving out the perchlorate portion, will give us 2. This 2 applies to the oxygen. And then 1 from the water. Hydrogen, we have 2. Again, leave off the... Well, actually, the perchlorate doesn't have a hydrogen, so excuse me there. So 2 hydrogens, and then 1 more, so that's 3. And the 2 hydrogens from water. The perchlorate, we have 1 unit and 2 units. So then just start balancing, working down this list that they've given us. The bariums, there's 1 of each, so then move to the next element down, which is oxygen. And actually, let me follow the order they're doing it. So they are going to balance the perchlorates next. So they put a 2, it's shown in this equation, they put a 2 in front of the HClO4, and when they do that, that changes the hydrogens to a total of 4 on the left side, and changes the perchlorates to 2. The next thing they've done here is to put a 2 in front of the water, which is shown here. That changes the hydrogens on the right side to a total of 4, so our hydrogens balance out. And the chlorate on the right side is already added 2. It's always good to check and make sure everything does work out. They've checked it with individual atoms, but just go through and check using this one, or you can do individual atoms. Barium, we have 1 on both sides. The oxygens that are not part of the perchlorate, we have 2 and 2 with the 2 in front of the water. Hydrogens, we have 2. 2 more is 4. And then 2 times 2 is 4. And the perchlorates, the 2 in front multiplies through, gives us 2. And we have 2 there as well. The best way to get better at balancing chemical reactions is just through practice, just doing it over and over and over. I believe we have a second type of balancing equation in 8.2. Read this along with me. Butyric acid, and it has another name of butanoic acid. The chemical formula is C4H8O2. Is one of many compounds found in milk fat. First isolated from rancid butter in 1869, butyric acid has revealed a great deal of attention in recent years as a potential anti-cancer agent. Write a balanced equation for the metabolism of butyric acid. And it's going to give us some information for what happens with metabolism. Just that assume the overall process of metabolism and combustion are going to be the same. In other words, reaction with oxygen to produce carbon dioxide and water. So we're going to start with our formula of butyric acid, add to that oxygen. This is the oxygen that is in the air we breathe. Anytime you burn anything, you're going to add oxygen to it. And that is diatomic oxygen. So make sure you put O2. Carbon dioxide is CO2 and water is H2O. And just read along the strategy with me. Begin by writing an unbalanced equation to represent the combination of reactants and formation of products as stated in the problem, and then balance the equation. So let's take a look at this. So here's our formula of butyric acid. It's an acid and it will be dissolved in water, so it has the AQ. Oxygen is a gas, so we have O2 gas. Carbon dioxide is a gas, and then water is going to be a pure liquid. And again, there's different ways that you can balance these. It doesn't have to be in this specific order. I usually like to balance the oxygens last, and I believe they do here as well. And I usually start with waters, but it looks like they started with the carbon atom. So we'll just follow along how this works in the slide. Excuse me. Balance the number of carbon atoms by changing the coefficient for carbon dioxide from 1 to 4. So we have 4 carbons in butyric acid. Putting a 4 in front of CO2, we'll put 4 carbons on the reactant side, 4 carbons on the product side. Then we can balance the number of hydrogen atoms by changing the coefficient in front of water from 1 to 4. So we put a 4 in front, and that will be this equation line here. That changes the hydrogens to a total of 8 on the right, and then we have the 8 in the butyric acid. Then finally balance the number of oxygen atoms by changing the coefficient for O2 from 1 to 5. So putting a 5 in front of O2, we have 2 oxygens in butyric acid. Then 5 times 2 is 10, so that will be a total of 12 oxygens. And then on the right side, we have 4 times 2 is 8, plus 4 more oxygens is 12. Double check and make sure that everything balances. So it said count the number of each type of atom on each side, verify the equation is properly balanced. We have 4 carbons, 8 hydrogens here, and 4 times 2 for 8. And then for our oxygens, we just saw that, but there's 2 and 10 more would be 12. And then here we have 8 and 4 is 12. And the third example is going to be identification. It states, determine whether each of the following equations represents a combination reaction, a decomposition reaction, or a combustion reaction. The strategy here is looking at each equation and then figuring out, do I have 2 things coming to 1? So in the equation in part A, it says 2 reactants, 1 product. And then B, you can see that you have 2 reactants and 2 products, but notice that it's plus O2. Plus O2 usually, represents combustion. And then the last one has 1 thing separating out into 2. So our solutions for these are fairly straightforward once you understand the difference between combination, which is 2 producing 1. Decomposition is usually 1 producing 2. And combustion reaction will be adding O2. And if it is a hydrocarbon or a carbon, hydrogen, oxygen type compound that you're burning, then you'll produce carbon dioxide and water. So for part A, we can see that it is combining, so it's combination. Part B, we're adding O2, producing carbon dioxide and water, so it is combustion. And then the last one we are separating out, and that would be a decomposition. Alright, so this is example 8.5. I actually had to go back and take out example 8.4 because the uh, slide creators, and these come from the textbook, there was a couple errors in it, and it wasn't worth showing you that with the errors just to add confusion. So, anyways, let's go through 8.5. Urea, which has the chemical formula of NH22CO, is a byproduct of protein metabolism. This waste product is formed in the liver and then filtered from the blood and extracted in the urine by the kidneys. Urea can be synthesized in the laboratory by the combination of ammonia and carbon dioxide according to this equation. And this is showing some space-filling diagrams here. And the nitrogens are blue, hydrogens are white, carbons are black, oxygens are red. And then here's our normal notation that we're familiar with. And this is already balanced for us. You could leave off the 2, but I guess you already know there's a 2 there. And you could practice balancing this and convince yourself that it is. But anyways, here's 2 moles of ammonia gas plus 1 mole of carbon dioxide gas produces 1 mole of urea and 1 mole of liquid water. Have a couple parts here. Part A, calculate the amount of urea that will be produced by the complete reaction of 5.25 moles of ammonia. And Part B, determine the stoichiometric amount of carbon dioxide required to react with 5.25 moles of ammonia. So now we're full-fledged into stoichiometry calculations, and it uses balanced chemical reactions and then our ability to calculate moles to grams and so forth. Our strategy here is going to be using the balanced chemical equation to give us conversion factors or molar ratios. And then we can use the periodic table to find the molecular weights and atomic weights of the components. So for part A, to find the moles produced of urea, we can do that from ammonia. Now we have 5.25 moles of ammonia. And let's see, that's given. And then from our balanced equation, we have 2 moles of ammonia on the reactant side that produces 1 mole of urea. And then our moles of ammonia cancel out. And then that will give us 2.63 moles of urea. So for moles of carbon dioxide produced, we can do that from ammonia, starting with 5.25 moles of ammonia. These are going to be our coefficients from our balanced reaction. There's 2 moles of ammonia, 1 mole of carbon dioxide. Moles of ammonia cancel. And then doing the math here, we get 2.63 moles of carbon dioxide. Okay. And I'll just give you a moment to read through this bottom. Think about it. Alright, if you need more time, just pause the video. Let's look at example 8.6. Dinitrogen monoxide, formula N2O, is also known as laughing gas or nitrous oxide, is used as an anesthetic, usually in dentistry. It is manufactured by heating ammonium nitrate. And this triangle represents applying heat. This would be a decomposition type reaction. So we have ammonium nitrate solid, you heat that, and we can isolate nitrous oxide, N2O, gas state, and there's 2 moles of liquid water. We're asked 2 things, A and B. Part A, calculate the mass of ammonium nitrate that must be heated in order to produce 10 grams of nitrous oxide. And Part B, determine the corresponding mass of water produced in the reaction. So read through the strategy if you want. If you want to just keep following along, we'll continue. So for our solution, starting with 10 grams of our N2O, we're going to use the ratio. The 44.02 is the molar mass of N2O. We set it up this way so that our mass cancels. This gives us moles of N2O. And then from our moles, this value is just rewritten here. We can use our values that are from the balanced reaction to go from moles of nitrous oxide to moles of ammonium nitrate, which is here. And then this is just rewritten, and we multiply by the molecular weight of ammonium nitrate, and then that gives us our mass. So major thing here is to go from mass to moles, you're going to use the molecular weights, which you just get right from the periodic table. And to calculate from moles to moles, you use your ratio from your balanced reaction, which would be these values that are in the front. 1, 1, and 2. So therefore, from 10 grams of nitrous oxide, we would need 8.2 grams of ammonium nitrate. So therefore, 18.2 grams of ammonium nitrate must be heated in order to produce 10 grams of nitrous oxide. Part B, starting with the number of moles of nitrous oxide determined in the first step. So we have 0.227 moles of, where is it, right here, of nitrous oxide. So we're starting with that. To go from moles of nitrous oxide to water, we use the coefficients from the reaction. There's 2 parts water formed from 1 part of the nitrous oxide. This gives us moles of water. And then we can use the molecular weight of water, allow the moles to cancel, and that gives us our mass of water, 8.18 grams. Nothing more to this than going from moles to grams and moles to moles. So just practice a few of these, and then I think you'll have a really good grasp on it. One thing you can do is use the law of conservation of mass, stating that matter can neither be created nor destroyed, to check your answers. So in this case, we have 10 grams and 8.18 is 18.2, so that actually works out. The next example, 8.7, just read along with me. Alka-Seltzer tablets contain aspirin, sodium bicarbonate, and citric acid. When they come into contact with water, the sodium bicarbonate, NaHCO3, and citric acid, H3C6H5O7, react to form carbon dioxide gas, among other products. And here's our balanced chemical reaction. We have a 3, 1, produces 3, 3, and 1. Okay. Big thing when you put an Alka-Seltzer into water, as many of you probably have done or have seen, you'll form bubbles. So the formation of the carbon dioxide causes the old trademark fizzing when the tablets are dropped into a glass of water. An Alka-Seltzer tablet contains 1.700 grams of sodium bicarbonate and 1 gram citric acid. Determine, for a single tablet dissolved in water, and we have 3 parts here to do, A, which ingredient is the limiting reactant, meaning which one is going to give, which one will be used up first, your weakest link. Part B, what mass of the excess reactant is left over when the reaction is complete. And part C, what mass of carbon dioxide forms. Oops, so let's just read through this strategy together. Convert each of the reactant masses to moles. So you got some masses here that you can convert to moles. Then we'll use our balanced equation to figure out conversion factors and ultimately see which one is limiting. Next, determine the moles of excess reactant remaining and the number of moles of carbon dioxide produced. And the last thing we'll do is use the appropriate molar masses to convert moles of excess reactant and moles of carbon dioxide to grams. Again, the wordy description is usually a lot more to wrap your mind around than actually just seeing it. So let's take a look at that. So here we have our sodium bicarbonate, 1.7 grams, and let's see, those are right here. And then we're going to use a gram of citric acid in a moment. The 84.01 is just adding up sodium, hydrogen, carbon, and 3 oxygens from the periodic table. We set this up so that grams cancels. This gives us our moles of sodium bicarbonate. 1 gram of citric acid, and then adding up all of these, we got 1, 2, 3 hydrogens here, 5 more, so that's 8. 6 carbons and 7 oxygens, all comes to a total of 192.12 grams. we set this up so that our mass in grams cancels, leaves us with moles. So we have these two values. So to determine which reactant is limiting, we want to calculate the amount of citric acid necessary to react completely with 0.02024 moles of sodium bicarbonate. So we have 0.02024 moles of sodium bicarbonate times our ratio from our balanced equation. We have 1 mole of our citric acid and 3 moles of sodium bicarbonate. This comes out to this value in moles of our citric acid. So the amount of citric acid required to react with this many moles of sodium bicarbonate is more than a tablet contains. So what that means is the citric acid is the limiting reactant. So it's going to be the one that's used up first. And the sodium bicarbonate is the excess reactant. You can work it out both ways so that you can see that if you wish. So to determine the mass of the excess reactant, which is the sodium bicarbonate left over, first calculate the amount of sodium bicarbonate that will react. So we have the 0.005205 moles of sodium bicarbonate. Here's our ratio from the I keep wanting to say periodic table. It's from the balanced equation, which are these values here. 3, 1, 3, 3, and 1. And this gives us this value in moles of our sodium bicarbonate. So 0.01562 moles of sodium bicarbonate will be consumed. That leaves 0.00462 moles unreacted. And we can convert the unreacted amount to grams by using stoichiometry again, just from the molecular weight of sodium bicarbonate. Moles cancel, and this takes us to grams. Now for part C, to determine the mass of carbon dioxide produced, first calculate the moles of CO2 produced from the number of moles of the limiting reactant, which is the citric acid consumed. So we start with moles of citric acid. We use our coefficients from the balanced reaction, 3 and a 1, and that gives us moles of carbon dioxide, which then again we can use the molecular weight of carbon dioxide, allow our moles to cancel, and this gives us our mass. So just an application here is just still using stoichiometry to calculate moles to grams and moles to moles, but then also looking at which one is used up first. A lot of times we need something that we can wrap our mind around, like making a sandwich. A lot of times this is used in textbooks and in PowerPoint slides. So if you're making a sandwich and you have a certain amount of pieces of bread, some cheese, and some meat, and you want to make a certain number of sandwiches, you can only make as many as either the pieces of bread you have, or cheese, or meat, assuming that you want to make a full sandwich. So if you have a whole loaf of bread, but you only have 2 pieces of cheese, and you want 1 piece of cheese per sandwich, the most you can make is 2 sandwiches. The cheese would be used up first. So you can think about that. To summarize our results here, so just give you a moment to let that marinate in your head by talking about sandwiches. If you're listening to this while you're hungry, then go ahead and stop and eat something and come back. Anyways, we know that citric acid is our limiting reactant, and we have 0.388 grams of sodium bicarbonate remains unreacted, and last thing is 0.6874 grams of carbon dioxide is produced. Alright, this is example 8.8. This is our last one. Aspirin, acetyl salicylic acid, C9H8O4. And if you take organic chemistry lab with me eventually one day, or even organic chemistry lab anywhere, one of the major labs you'll do is you'll get to make aspirin. And you'll do this exact reaction, so it's pretty cool. This is the most commonly used pain reliever in the world. It is produced by the reaction of salicylic acid, as shown here, and acetic anhydride, according to this following equation. And this is already balanced. It's 1 mole of salicylic, 1 mole of acetic anhydride. 1 mole of acetyl salicylic acid and 1 mole of acetic acid. So these are really nice. A lot of reactions in organic chemistry are 1 to 1 to 1 to 1, so the molar ratio is pretty easy. And when you do the organic experiment, if you end up taking organic chemistry lab, you'll need to be able to do this exact calculation that you are learning now. And this is going to be an extension of stoichiometry, where you'll calculate a theoretical yield and a percent yield. So in a certain aspirin synthesis, we have 104.8 grams of salicylic acid and 110.9 grams of acetic anhydride combined. Calculate the percent yield if 105.6 grams of aspirin are produced. So our strategy here is to convert the reactant grams, which are given, to moles, and then figure out which one would be used up first, which is the limiting. Then use the balanced equation to determine the moles of aspirin that can be produced. Convert to grams for the theoretical yield. The theoretical yield will be a mass in grams of the best possible scenario of how much you could produce if you got 100% conversion. Use this and the actual yield given to calculate the percent yield. The actual yield would be how much you produced in your experiment, which would be this value. All right, so let's take a look at these numbers. So starting with our mass of our salicylic acid, we have our molecular weight of it. Hopefully this is calculated right. 7 carbons, 6 hydrogens, 3 oxygens. Mass cancels, leaves us with moles. And here we have our acetic anhydride, 110.9 grams of that. Here's our molecular weight. Mass cancels, and that leaves us with moles. And from the equation, because the two reactants combine in a 1-to-1 mole ratio, the reactant present in the smallest number of moles, in this case is the top one, so it's 1.086 versus 0.7588, is going to be the limiting reagent, and that is the salicylic acid. According to the balance equation, 1 mole of aspirin is produced for every mole of salicylic acid consumed. So it's real easy to go from moles to moles in this case, right? Therefore, the actual yield of aspirin is 0.7588 moles. So we take moles of salicylic times, if you wanted to show it, you'd have 1 mole of the acetylsalicylic acid over 1 mole of salicylic. Moles of salicylic cancel, and you get your product, if you can visualize what I just went through. We can convert to grams using the molecular weight of aspirin, arranged in this format so that moles cancel. You multiply here, and we get 136.7 grams of C9H8O4, which is our aspirin. So this is our theoretical yield. That's the best that we can get. Now our actual yield is 105.6. You'll take actual divided by theoretical times 100 to get a percent yield. So we're going to take our 105.6 divided by our theoretical, 136.7, multiply by 100, and that comes out to be 77.25%. And one thing to remember is make sure you've used the proper molar masses, and remember the percent yield could never exceed 100%. If it exceeds 100%, then that is disobeying the law of conservation of matter. If in reality, when you actually do something like this in a lab and you get a percent that's greater than 100, more times than not, what that would actually mean is that your sample is wet and that it hasn't been given enough time to dry and it has too much water in it. So remember that for one day when you have to do this in organic lab, for those of you that need to take it. So that ends chapter 8, and I'll be back with another video in chapter 9 next week. Thank you.